Okay, welcome to lesson 2.3, graphs of polynomial functions. Today we're going to look at higher degree polynomial functions. We've been looking at the quadratic, which is the second degree, where f of x equals sum a times x to the second power plus some bx plus c. That was a quadratic, and this has a degree of 2 because the highest power of x is 2. So that's its degree. A lot of vocabulary in today's lesson. In fact, a lot of vocabulary in all lessons, especially today's. So the definition of a polynomial function is a function in the form f of x equals some lead coefficient, some number times x to some power, plus some other number times x to a power lower than that, plus plus some number times x to the first, plus some constant. Okay, if this was a 3, then this would be a 2, and this would be a 1 and a constant, okay? It's just very formal looking, but not to be afraid of it. Standard form, we go from the highest power on x and down. N is a non-negative integer, and each a is a real number. A real number. Leading coefficient. The lead coefficient is the constant part of the first term, the term with the x raised to the highest power. Okay? If you were just to read this without my explanation, yes, I can understand. It would be challenging to some of us. Okay? But having that explanation and a few examples shouldn't be too hard. This, the highest power on x, is the fifth power. It makes it a degree 5. The leading coefficient is the negative 2. It's the coefficient with the highest power of x. Now you're saying, but Mr. DeFranzo, 5 minus 1 is 4. Well, there's an x to the fourth in here. It's just that it's times 0, so we can't see it. Do you understand? There is a 0. X to the fourth. There is a 0 x squared here. Okay? Another example. X to the third plus 6x squared minus x plus 7. This is a third degree polynomial with a lead coefficient of 1. Finally, another example. F of x equals 14. This is the lead coefficient, and this is a degree 0 polynomial because it has an x to the 0. Remember that when we study exponents, anything raised to the 0 equals 1, right? So 14 times 1, 14. Graphs of polynomial functions are continuous. That is, they have no breaks, holes, or gaps in the graph. They are smooth curves. Here's the graph of f of x equals x cubed minus 5x squared plus 4x plus 4. Smooth curve. The arrow on the end indicates that it continues on in that direction infinitely. This graph is not a polynomial because it is not continuous. It has this break in it. This is not a polynomial because it is not a smooth curve. Okay, continuous, not continuous. Continuous, but polynomials are functions, smooth, rounded terms. Graphs with points or cusps are not graphs of polynomial functions. See this pointy thing here? That's not a polynomial. This is smooth. That's not smooth. This is a polynomial. Not continuous is not a polynomial. Not smooth is not a polynomial. Polynomial functions of the form f of x equals x to the n, where n is some number greater than 1, are called power functions. Power functions. Okay? X squared, that's a power function. X to the fourth, that's a power function. X to the third, that's a power function. If this power is an even power, then the graph is going to look something like that graph of x squared. See, x to the fourth, it's going to continue up at a steeper rate, and the bullnose down here gets a little bit wider. Okay, but it has the same shape, and it has what we call the end behavior of a quadratic. X to the third, as x increases, y increases. As x decreases, y decreases. Over here, as x increases, y increases, and as x decreases, y increases. Okay? Just like x to the fourth looks like x squared, x to the fifth looks something like x to the third. Again, just this curve down here gets a little bit squarer, a little bit more bullish. Okay, so gets the graph of x equals negative x plus 2 to the fourth. Okay, well, we already know how to shift, flip, and all that good stuff. Okay, so this is a shift of the graph of y equals negative x to the fourth, 2 units to the left. Shifts 2 units to the left. And it's a flip of positive y equals positive x to the fourth. It's a flip over the x-axis. So we can start with y equals x to the fourth, flip it, and then move it to the left 2, and we have our graph. Just that simple. Just like x squared would have been if we had negative x plus 2 squared. We do the same shift and translation. We want to test the lead coefficient. Okay, again, our formal definition. The lead coefficient, the constant part of the x term where it has the highest degree, the highest power. We find that it grows positive or negatively without bound, depending upon the sign of the leading coefficient. In other words, if this was positive and it's even, well then it's going to grow without bound, without limit, up. As x gets bigger, y gets bigger. As x gets smaller, y gets bigger. As x approaches infinity, in other words, goes up and up and up, then y goes up and up and up and up. This is when it's even. When it's odd, like some of you watching this, well then you have the same situation here. As x grows without bound, y grows without bound, but as x gets lower towards negative infinity, y also gets smaller towards negative infinity. This is when it's odd. Again, odd like some of you watching now. Did he actually say that? No, I didn't say that. They've done a voiceover and somebody is trying to get me in trouble. Look, here's the graph. N odd. A sub n negative. A sub n positive. Remember, if that first term, if the sign switches, we do a reflection across the axis, and we see that it changes again with the even functions. we do a flip, we see that the direction changes. So if it's an even function, it has this end behavior where both sides are going in the same direction. If the first coefficient is positive, it's growing up. But if the first coefficient is negative, the lead coefficient, negative, it's going to go down. Okay, so let's describe the right-hand and left-hand behavior for the graph of f of x equals negative 2x to the third plus 5x squared minus x plus 1. Well, we know if it was positive, it would look something like this. But because it's negative, we know that it's flipped. So it's going to look something like that. And so as x gets lower, f of x is going higher, but as x gets higher, f of x is going lower. That's because it's negative. The lead coefficient is negative, and it's odd. So, again, oh look, my curve is pretty good compared to theirs. Okay, a real number a is a zero of a function if y equals f of x. If and only if f of a equals 0. It's a zero. We've used terms interchangeably. A factor, an x-intercept, a solution, a zero. I've been over this in class with you. Okay, the zero. A is a solution of the polynomial. X minus a is a factor of the polynomial. A comma 0 is an x-intercept. The following statements, these are all equivalent statements. They all mean the same thing. So when we're talking about a zero, we're talking about what makes y equal 0. Y equals 0. And y equals 0 when it is an x-intercept. And these are where we get the factors, by taking that letter, that value here for a, and going back. Remember, we were just doing this last night. We were getting like x equals negative 2, and we had to figure out the quadratic. X equals 4, x minus 4 equals 0, and we found the two factors. We found the two factors when these were zeros, okay, or solutions. Turning point of a graph. It's going to have, let's see, at most n minus 1 turning point. So if it's x squared, it has one turning point. Right? It's to the second power. It has n minus 1. It has 2 minus 1 turning points. If it's x cubed, it's going to have 3 minus 1 cubed turning points. If it's to the fourth, it's going to have 4 minus 1 turning points. Up to. If it's to the fifth, you might have something like this. 1, 2, 3, 4. 5 minus 1 turning points. Okay? And it's going to have at most n zeros. Find all the real zeros. X to the fourth, x to the third, x squared. Well, you have to factor it completely. And you can see right here we have a common factor of x squared. You take that out, factor x squared out of this, and you're going to get x squared times x squared minus x minus 2. And needs to multiply to give you 2 and add to give you negative 1. Or multiply to give you negative 2 and add to give you negative 1. So it's negative 2 and positive 1. And there's how you factor the quadratic. And so x squared times x plus 1 times x minus 2. Okay? Now we know that x squared equals 0, x plus 1 equals 0, and x minus 2 equals 0. So there's a 0 at x equals 2, there's a 0 at x equals negative 1, and you have a repeated 0 at x equals 0. What this looks like when you graph it is this is going to be a place where it touches the x-axis, and these other places are where it will actually cross the x-axis. So this would be 0, this would be negative 1, this would be 2. Except I drew it as though the lead coefficient was negative, so I have to do this the exact opposite way. So it would touch here. It would look something like that, because these are the zeros. Let's see what they've said. Well, now look at that. You see, you can do this. If you understand these basic things, and everything is following the same logic, it's all following the same logic, you can be able to see these graphs too. I know some of you already do. Graph shows that there are 3 turning points. Since the degree is 4, this is the maximum number possible. Turning point, turning point, turning point. Okay, pause here, come back for part B. I'll do some homework problems in part B.